Ever wonder why some AI models outperform others when given more computational power? Or how researchers predict a model's accuracy before training it? Today, we're unpacking a groundbreaking study that reveals how machine learning models scale, how their performance evolves with more data, bigger architectures, and greater compute. Spoiler, one model, MaMMUT, dominates its competitor, CLIP, when resources hit a critical threshold. Let's start with the fundamentals. Imagine training a model to recognize objects in images. You could feed it more data, boost its computational power, or expand its architecture. But how do these factors actually affect performance? The researchers here turn to scaling laws, mathematical formulas that predict how a model's error rate drops as you increase compute, data, or parameters. Think of it like a recipe. If you add more ingredients, data, or compute, how much better does the dish model performance get? The study focused on two models, CLIP and MaMMUT, testing them on tasks like image classification, ImageNet, and text-to-image retrieval, MSCOCO. They varied three key factors: model size, number of parameters, dataset size, and image patch resolution. But the real breakthrough came from analyzing how performance improved with compute. Here's where it gets fascinating. The team discovered that performance follows a power law, a curve where gains slow down as you add more resources. But there's a critical detail. At low compute levels, models aren't perfect, but they're not terrible either. Why? Because even without training, a model might guess based on data distribution. It's like a student who guesses on a test. They might get some right by chance. To account for this, the researchers introduced a baseline error term into their equations, representing this random guessing. Then they measured how each model's error rate dropped as compute increased. The twist: MaMMUT outperformed CLIP after a certain compute threshold, around 1010 to 1011 GFLOPS. That's like upgrading from a basic calculator to a supercomputer. Below that threshold, CLIP was better, but once you hit that sweet spot, MaMMUT zooms ahead. Why does this matter? Scaling laws help researchers allocate resources wisely. If MaMMUT becomes more efficient with compute, it's a game changer for high-stakes applications like medical imaging or autonomous vehicles. The study also showed this trend held across datasets, datacomp, RealAION, DFN, and tasks, proving MaMMUT's versatility. But how did they validate these trends? They used confidence intervals, error bars that show how reliable their predictions are. By extrapolating models to unseen compute budgets, they confirmed MaMMUT's edge wasn't a fluke. In fact, their predictions for a 12.8B sample dataset matched real-world results almost perfectly, even without training on that exact data. Now, let's dive deeper into the models themselves. The study also compared vision transformers, ViT, with an advanced variant, mammut-ViT. Think of ViT as a standard neural network, while mammut-ViT is like a more sophisticated version with more parameters, the puzzle pieces that let the model learn complex patterns. For example, a mammut-ViT B16 has 290 million parameters, V's 150 million for its standard counterpart. More parameters mean more computational power, measured in GFLOPS, operations per second, but also higher energy and cost. The data shows a clear trend. As models grow in size, width, depth, their error rates drop. Take mammut-ViT L14, which achieves 39.14 GFLOPS with a significantly lower error rate than standard ViT. This efficiency is key. More data equals better, more consistent results. When tested on 1.4 billion images, accuracy jumped from 76% to over 80%, with tighter confidence intervals. It's like practicing a skill. More practiced data equals better, more reliable performance. But this wasn't a solo effort. The researchers relied on open-source communities and shared datasets to test their ideas. Without transparency, it's like solving a puzzle with half the pieces missing. And let's not forget the real-world impact. These scaling insights could shape future AI systems, making them faster, more accurate, and more accessible. So what's next? As compute power grows, models like MaMMUT and mammut-ViT will push the boundaries of what's possible. But the real question is, how will we balance power, efficiency, and ethics as these systems evolve? Stay tuned for more deep dives into the cutting edge of AI research.